It's my pleasure to introduce Charles Kuster. He'll be talking about dual-pol signatures of QLCS Mesovortices. Go ahead, Charles.
All right, thanks for the intro, Mike. I'm excited to be here and talking with you all today about some work that myself, as well as Keith Sherburne, Vivek Mahale, Jason Schauman, Terry Shore, and a student, Olivia McCauley, have been working on the last couple years, and really just looking at some dual-pol and a couple single-pol radar signatures associated with QLCS mesovortices. I do want to point out this QR code down here at the bottom. If you scan that, it'll take you to a somewhat interactive presentation where you can kind of step around and look at some of the results. You can follow along with what I'm talking about in real time, or if you want to look at some other things or generate some questions perhaps along the way, feel free to do that. And I'll also have this QR code up on the last slide of the presentation as well. I plan to cover a lot of material. We looked at a lot of stuff. We got a lot of stuff to share. So I don't want this to be just 35-40 minutes of me talking at you all. So if anybody has a question at any point in time, you feel free to interrupt or do the, I'm not sure if I can see who raises a hand, but any way that you feel comfortable asking a question, I definitely encourage you to ask those at any point in time, or they can be done at the end of the presentation as well. But definitely interested in feedback and discussion about some of the stuff that we're doing as well. So we'll go ahead and jump in. The first thing to do is, of course, thank the entire research team. Everybody brought just a really unique set of skills to the project, and definitely would not have been able to do this work without each and every one of them. Really, the motivation behind our work was looking at whether there's any dual-pol signature, which is our focus. We also did look at a couple single-pol signatures, but really focused on those dual-pol signatures. And are there any of them that are worth adding to the Mesovortex warning system? Just a quick little review on the Mesovortex warning system. It's basically a framework that takes in environmental and radar-based factors to give some warning guidance for QLCS mesovortices. Really, the biggest summary or best rule of thumb would be if you have the 3 ingredients met, which is a surge in the convective line, balanced or slightly shear dominant regime, as well as the 0 to 3 kilometer bulk shear vectors being 30 knots or greater. And there's some wiggle room with these, and I'll mention that here in a minute. But basically, if you have the 3 ingredients met, plus more and more confidence builders and nudgers, which are some of the radar-based signatures, then there would be a higher confidence in a tornado warning. So this is a really good framework that is already out there, been developed by National Weather Service forecasters. And so we're really just looking to plug into this existing framework already. Outside of the tornado debris signature, dual-pol data haven't really yet been incorporated into this system. And so that's something that we really wanted to look at and see if there was use there. For these dual-pol signatures, are they common with mesovortices? Is there any connection between the magnitude of the radar signature and the strength of the mesovortex? These are all questions that we wanted to answer. And then we also looked at those questions with 2 single-pol radar signatures as well. So in terms of our analysis, we looked at 167 mesovortices in total, about 20 more tornadic than non-tornadic mesovortices. For all of the mesovortices, the 3 ingredients were roughly met. Like I said, there was some wiggle room, so I didn't have a hard cutoff of 30 knots, but at least roughly the 3 ingredients were met. If they weren't met, then the mesovortex wasn't included in the analysis. But it is relatively unusual to have mesovortices, especially tornadic ones, forming where the 3 ingredients are not met. And for all of our analysis, we wanted it to be applicable in operations right now. So we didn't use any algorithms. We didn't calculate area of the ZDR column, even if ZDR column area does seem to be useful, especially in supercells. We wanted to focus in on what could be applied right now. So for our analysis, basically what we did is we used a cursor readout and a radar software and just tracked the maximum value of these various radar signatures over time. We do have a pretty good representation of mesovortices across the country, as well as from the cool and warm season. We have them at various ranges from the radar and across a pretty wide spectrum of near storm environments. So sample size is, won't call it small, but it's kind of medium, 167 mesovortices. So can't say exactly how representative all these results are, but they should be decently representative. Currently, this work is in its second round of peer review, so it is in that process as well. But since this is, of course, ongoing work and plan to keep doing it, feedback is always welcome. So if you think something could be done better or something added or anything like that, I'm always interested in hearing y'all's perspectives. So I really just want to start off, after getting that quick background stuff out of the way, with the conclusions. So I'm not going to hold anybody in suspense. We're just going to go ahead and jump right into what we found. And the first one is that all of these radar signatures are not silver bullets. They can't stand alone by themselves and drive a warning decision. Just like with the mesovortex warning system, it's all about building the confidence and giving guidance for warning type, maybe even polygon placement, but none of these signatures that we're going to talk about can be used by themselves to issue warnings or even come to any kind of decision by itself. So the first radar signature, and I'm going to go into defining all of these more, but I want to get the conclusions out here to start with. We looked at a radar signature called a KDP drop, which is likely associated with a descending rear inflow jet, and therefore maybe surges in the convective line. We found that that signature was very common with mesovortices and could also give some indication of where a mesovortex is about to form. We also looked at KDP cores at the 0.5 degree elevation angle and at the elevation angle closest to the melting layer. And these really turned out to be what I think are the best, quote unquote, best radar signature of all the ones that we looked at, because they're present with a lot of mesovortices, and they also had the best connection between radar signature strength and mesovortex strength. ZDR columns, a little bit of a different story. They were present with a lot of mesovortices, but they don't appear to provide much information about how strong a mesovortex is or is about to be. We used a threshold of 50 dBz for looking at -20C reflectivity cores, and I'll go into this more in the future, but that's not a good threshold to use. It works for supercells, but QLCSs, as we might expect, the updrafts tend to be a little bit weaker, and so that threshold just wasn't a great threshold to use, and we learned that as we went through the process. We also looked at spectrum width at the 0.5 degree elevation angle, and there were some connections between the magnitude of the spectrum width and the mesovortex damage or tornado potential. So this was a good signature to use, but like I'll mention more in the future, it does develop around the same time as the mesovortex, so not a lot of predictive capabilities there, more of a diagnostic signature. And then trends. We, through input from some of the research team, trends are really important. So we dove into looking at trends, and the KDP cores once again had some interesting results there, especially with the low-level KDP cores. There was a difference in the trend between tornadic and non-tornadic mesovortices. So tornadic mesovortices had strengthening low-level KDP cores, non-tornadic mesovortices had weakening low-level KDP cores. We looked at the environment using RAP data, and for the most part didn't see a whole lot, but there are a couple exceptions that I'll go over. But for the most part, not a lot of strong connections between the radar signatures themselves and the environment in which they were occurring. And then range, we did want to look at range and see how that affects all of the results, and the range from the radar does matter. The further away you get from the radar, it looks like there will be less utility in using the signatures to anticipate mesovortex intensity, but the radar signatures were still present with a lot of mesovortices regardless of the range. So they should still be present with the mesovortex regardless of the range. So now we're going to go into each one of these conclusions in a bit more detail. Obviously, this isn't the last slide of the presentation, but I wanted to go ahead and put all this out there so we can have a starting point to go from. So KDP drop. First thing to do is just sort of point out what a KDP drop is. It's an area of low KDP that's just behind the main convective line, and it kind of eats into or erodes away the higher values of KDP along the updraft downdraft convergence zone. This signature, like I mentioned, it's associated with descending air in the rear inflow jet. So as that air descends, it warms, we get evaporation, and that's why the KDP lowers. KDP is actually really sensitive to evaporation. So this radar signature can really stand out. It's in the same location and idea as the Z drop, which is highlighted in the animation as well. And that Z drop is one of those confidence builders within the mesovortex warning system. I did want to point out a couple other examples of what a KDP drop might look like. The one on the previous animation was kind of a big, semi-obvious KDP drop. They can also be much smaller. So I've got a really kind of small, subtle KDP drop here. You can also see it ever so slightly and subtle in the reflectivity as well, with a little Z drop, just that slight lowering of reflectivity behind the main convective line. And then this, if we zoom out, same example, just to give some perspective. These white lines are counties, and so there's just a really small signature right there in the middle. So these can take on lots of different shapes and sizes, just like some of the reflectivity features in the mesovortex warning system. But we found that this signature was interesting because one of these preceded almost every single mesovortex that we looked at. So right around 95% of our mesovortices were preceded by a KDP drop. Now that's tornadic and non-tornadic, both had really high numbers. So not necessarily saying, okay, yeah, I see a KDP drop, it's going to be a tornadic mesovortex. It's more like, okay, I see a KDP drop, maybe there's going to be a mesovortex soon. We also found that there was a preferred location relative to the KDP drop for the development of a mesovortex. So basically, we just roughly divided the KDP drop in half and said, all right, if a mesovortex forms anywhere over here, that'll be on the left side of the KDP drop. And if a mesovortex forms anywhere over here, that would be on the right side of the KDP drop. So you can see that a majority of those mesovortices did form on the left side of the KDP drop. About 75% or so formed on that side of the KDP drop. And you can see that in the example here. This is the primary mesovortex for this particular screenshot. This thing produced an EF2 tornado. It's forming over here on the left side of the KDP drop. This particular example, and there's probably some horizontal, well, there is some horizontal shearing instability going on here, but there were multiple mesovortices that formed all down the line. And so we also have a mesovortex forming just on the right side, slightly on the right side of the KDP drop. And then another one down here. This is where things get a little bit subjective. Do we say that this mesovortex is associated with this KDP drop? Is there maybe another KDP drop in here somewhere? This was one of those cases where I was like, okay, this is a little bit uncertain. It's a little bit displaced from this KDP drop. So I actually said that this mesovortex was not associated with a KDP drop. So that falls into one of the 4% that did not occur with a KDP drop. And so I thought this was a good example to show because you kind of have everything across the spectrum in this particular case. So moving on from the KDP drops, we have another signature in KDP, which is a KDP core. We looked at these cores at two different heights. So this animation is showing an example of a mid-level KDP core. Basically, it's just an area of enhanced KDP, typically 1 or higher. And we're looking at the elevation angle either at or below the melting layer. We're doing that because I think this is a signature that is indicative of melting and therefore cooling within, say, a downdraft or within a portion of the QLCS. And I'll show a conceptual model here in a moment, but that can maybe drive a stronger downdraft and then increased convergence afterwards. So this is mid-level KDP cores. They are very close to the rear inflow jet, either embedded or on the edges of those rear inflow jets. Low-level KDP cores, same idea, where you have just an area of high KDP within the QLCS. There are other KDP cores present in these animations. The one that I'm highlighting is just the one that is associated with the tornadic mesovortex in these animations. So that's why only one of them is highlighted. The other KDP cores were associated with a weak mesovortex. And then there are also situations where you have KDP cores not associated with any mesovortices. Those would be what we could call false alarms. All of the radar signatures had those, but they were, at least in our examples, relatively limited when the three ingredients were met. Maybe somewhere between 10 to 25% of the KDP cores would be considered a false alarm where the three ingredients were met. So they do exist without mesovortices, but they do frequently exist with mesovortices, including this one that you see here. Now, in terms of that conceptual model, why did we want to look at these KDP cores? Basically, I in the past, I've done a lot of work with downbursts, and these KDP cores look to be a good downburst precursor signature because they are indicative of things like precipitation loading and melting hail near the melting layer. So that's basically just things that are going to drive a stronger downdraft. So we applied the same idea here. All right, so we have a mid-level KDP core that's strong. It means we could have a stronger downdraft because of that precipitation loading and that cooling. Okay, so what happens when that stronger downdraft reaches the surface? Well, we should have stronger outflow and a stronger localized surge where that stronger downdraft hits the surface. So with that stronger outflow, we then have stronger convergence at the updraft, downdraft convergence zone. Where you have that stronger convergence, you can then have a stronger low-level updraft. That stronger low-level updraft can then cause more stretching of existing vertical vorticity, and therefore you have, in theory, a higher mesovortex potential. So this is the conceptual model behind these KDP cores and why we looked at them in the first place. And there are some promising results, I think, with these KDP cores. So the low-level and mid-level KDP cores preceded most of the mesovortices that we looked at. So your low-level KDP core is here in the first column. About 85% or so of mesovortices were preceded by a KDP core. I'm sorry, low-level KDP core is the left column. Right column is mid-level KDP core. About 75 to 80% were preceded by that mid-level KDP core. And then low-level KDP cores, about 85% were associated with a mesovortex. As you might expect, the mid-level KDP core develops first, and then it descends and reaches the surface a few minutes later. So these low-level KDP cores, in terms of timing, they develop much closer to the time that the mesovortex develops, whereas the mid-level KDP cores are going to precede the mesovortex by around 10 minutes or so. And then some of the most encouraging things that we found was in the magnitude of the KDP cores. I've got lots and lots of violin plots, which are what these funky red blobs are. So I just want to describe what they are. Basically, the violin plot is showing the distribution of all of the different observations that we had. So the wider this red area is, just means that there are more observations at that point. Down here where it's really, really narrow, it means there's just a couple of observations at this particular magnitude of KDP core. And then I also overlaid the more traditional box and whisker plots just for reference, just give some more context to it as well. So box and whisker plot, this would be the median, and then each edge of the box is the 25th percentile on the bottom and the 75th percentile on the top. And any of the outliers are shown here in the black dots. So basically what we can see from this is looking at mid-level KDP cores. When we split them out by the strength or impacts of the mesovortex, if you will, the KDP cores tend to be stronger when you have more impact. So upper left here, we're looking at tornadic versus non-tornadic mesovortices. You can see that in general, there are higher values of KDP for those tornadic mesovortices versus those non-tornadic mesovortices. Same thing for damaging mesovortices. So either a wind damage report or a tornado report versus non-damaging mesovortice, which means no storm report whatsoever. Even looking down here, there's kind of this slow increasing trend as you go from non-damaging mesovortex to a mesovortex that produces at least an EF2 plus tornado. And then the last bit down here on the bottom right, obviously there are limitations with storm data. So we wanted to also look at mesovortex strength separated from storm data. So we looked at max mesovortex rotational velocity. Of course, there are limitations with storm data. Really, there's no perfect method, but we also do see an increasing trend where as the rotational velocity of the mesovortex increases, which is along the x-axis, the distributions get stronger for the KDP core, which is on the y-axis. And I do want to mention that there's overlap. So you can see that we have values of KDP cores. If we pick, about 4.5, the value of 4.5 in KDP sits relatively close to the median of non-tornadic. It's below the 25th percentile of non-tornadic, but there are tornadic mesovortices that are occurring in, where the distributions overlap. So like I mentioned early on, no silver bullet. All of these things are just confidence builders to get to a final decision point, but they're not a standalone decision point. We saw very similar results with the low-level KDP cores. So now we're looking at 0.5 degree elevation angle. The differences here were actually bigger than for mid-level KDP cores. So still seeing nice separation between the distribution of tornadic and non-tornadic mesovortices, damaging and non-damaging mesovortices. The increasing trend from non-damaging to EF2 plus is even stronger, is even more clear with these low-level KDP cores. So we're thinking that this is a promising dual pole signature that could be potentially something to add to the mesovortex warning system as a confidence builder or nudger. Moving on to ZDR columns. ZDR columns are an updraft signature. So basically, if you have an area of positive ZDR, we define it as 1 or greater, somewhere above the melting layer, that's showing you where there are liquid raindrops and whatnot being lofted up above the melting layer by the updraft. For ZDR columns, we did find that a pretty good chunk of our mesovortices were preceded by these ZDR columns, about 75 to 80% once again. The big difference when we're talking about the other radar signatures, especially the KDP cores, is if I throw up all these distributions, now we don't really see much in the way of differences between the ZDR column, either height or magnitude. Didn't really matter what we looked at. There weren't much in the way of differences between those tornadic mesovortices and non-tornadic mesovortices. Even damaging versus non-damaging. The distributions are pretty similar. And these p-values are showing the statistical significance. Once this gets below 0.05, we say it's statistically significant. So we're nowhere close to 0.05 here or here. With the KDP cores, we were way below 0.05. So not only were there differences, but they were statistically significant. Here, when we look at them, don't see differences, and they're not statistically significant. Same idea with looking at mesovortices that produce different tornadoes rated higher on the EF scale, not really seeing any differences here. And then as the rotational velocity increases, still don't really see much in the way of differences there. It's possible, kind of our hypothesis as to why this is that a ZDR column might tell you more about the mid and upper level updraft strength as opposed to the low level updraft strength. And the low level updraft strength is probably the most important thing for stretching that vorticity. And so maybe that's why we're not seeing a great connection here between the ZDR column strength and the impacts of the mesovortex. Looking at the -20C reflectivity cores, another potential updraft signature that's used relatively commonly in various situations. Here, when we apply that 50 dBz threshold, didn't work out so well because less than 50% of the mesovortices that we had were associated with or preceded by a 50 plus dBz reflectivity core. And then similar idea when we look at the distributions, we don't see a lot of relationship between the magnitude of the -20C reflectivity core and the impacts of the mesovortex. Two caveats to that. There were statistically significant differences between the -20C magnitude between damaging and non-damaging mesovortices. And then also because of our 50 plus dBz threshold, our sample size is pretty small. So I think this is an area for potential future work, maybe look at some different thresholds, but that's something that we haven't gotten to yet. So for now, all I can really say is that 50 dBz is not a good threshold to use in these situations, and that's not particularly surprising. And then for our last single pole signature, we looked at spectrum width at 0.5 degrees and basically saw these areas of enhanced spectrum width. So spectrum width generally above 7 meters per second, that is co-located with the mesovortex. Now this isn't surprising to see this. You'd expect higher spectrum width where you have those turbulent motions and lots of different things going on within the mesovortex. You can see these little areas of enhanced spectrum width, with each one of these three mesovortices. They do form at about the same time as the mesovortex, which once again isn't surprising. So a little bit more of a diagnostic than predictive signature. But they were associated with many of the mesovortices that we saw, 85%, maybe even more of the mesovortices. We did also see differences in the magnitude of the spectrum width between tornadic and non-tornadic, damaging and non-damaging mesovortices. So that was interesting, and those were statistically significant. The kind of drawback to these is that they do develop at the same time as the mesovortex, so more of a diagnostic signature than predictive, whereas the KDP cores, they're at least developing 1 to 3 or 4 volume scans prior to the mesovortex. Another thing I wanted to point out is with the area of a spectrum width, we didn't see an increasing trend in the spectrum width magnitude, even as the tornado EF scale rating increased. So that's different than those KDP cores. So I do think that the KDP cores are maybe a quote unquote better signature than these areas of enhanced spectrum width, just because of that slightly stronger tie to the impacts and maybe strength of the mesovortex. And spectrum width was impacted a little bit more by range from the radar than the KDP cores were. It looks like maybe within 70 kilometers, which I think is in the 50 nautical mile range or so, maybe a little bit less than that, is where these signatures are most useful. All right, so trends. Super important to look at trends. This is basically just showing the observations of mid-level KDP cores for tornadic in the red line and non-tornadic in the black line over time relative to the mesovortex development. So 0 here is when the mesovortex developed. Going to these negative values, that would be before the mesovortex developed. Positive would be after. Basically, we took all of the volume scans. There were near 1,000 of them. And we just averaged them together for all of the KDP cores based on when they occurred relative to mesovortex development. And that's how we produced these plots. So when we look at the trends, don't really see much in terms of different trends between the non-tornadic and tornadic mesovortices. It's kind of noisy. There's just not a lot clear to see. One thing that we can see, and the violin plots, really showed this, was the tornadic mesovortices are stronger, or I'm sorry, the KDP cores associated with the tornadic mesovortices are stronger than the non-tornadic mesovortices. And you can see that with these box plots as well. We did the same idea, but we split it out into 5-minute bins, time intervals. So once again, this 0 right here would be when the mesovortex is developing. Red is the tornadic mesovortices. Blue are the non-tornadic mesovortices. You can see basically for all times, the median of the tornadic mesovortice KDP core is higher or very close to the 75th percentile of the non-tornadic KDP cores. So at all times, the mid-level KDP cores are stronger for tornadic mesovortices than non-tornadic mesovortices. When we look at the low levels, we see the same idea where the median for the KDP cores for tornadic mesovortices are higher than the non-tornadic mesovortices, and that gets more apparent with time. And that more apparent with time piece, that's a trend. This was cool to see. So now when we look at the trends in the strength of the KDP cores for tornadic and non-tornadic mesovortices, we see a difference. So for tornadic mesovortices, the low-level KDP core tends to intensify or strengthen with time. For the non-tornadic mesovortices, it tends to stay about the same and even weaken a little bit with time. So that's a difference in the trends that might, in and of itself, be a confidence builder, where if you see a strengthening low-level KDP core and one that's stronger, that could be a good confidence builder, perhaps for anticipating a tornadic mesovortex. I also wanted to show the trends for the low-level area of enhanced spectrum width. Once again, you can see in overall that the spectrum width is higher for the tornadic mesovortices than the non-tornadic mesovortices. That can be seen in this line plot as well as in these box plots. But similar to the mid-level KDP cores, there's not really a difference in the trends between tornadic and non-tornadic. They tend to behave in similar ways. So moving on to the near storm environment. We looked at lots of different environmental parameters, lots of different shear, measures of shear, measures of instability, looked at LCL, LFC, the Craven-Brooks significant severe parameter. We looked at lots of different things, and we didn't see very many relationships between the radar signature magnitude and the near storm environment that they occurred in. There are a couple of potential reasons for this. Maybe the RAP data doesn't have a small enough spatial resolution. There could be potentially some convective contamination impacts, perhaps. And then another possibility is that there's just not a strong connection between the environment and some of the radar signatures that we looked at. But a couple exceptions. I think this one's not super surprising, but we saw taller, stronger ZDR columns where there was stronger instability. So in general, stronger instability, you'd expect a stronger updraft and therefore a stronger, taller ZDR column. So you can see this violin plot is just breaking it down based on the median of ML Cape, which was 1,013 joules per kilogram. So if we had an environment where the ML Cape was above the median, the ZDR columns tended to be taller than in environments down here where we have the ML Cape below the median. And these were statistically significant differences once again. Now I do want to point out, so I talked about convective contamination. One way we tried to address that is we looked at close to the time of the mesovortex, so that's kind of the 0 hour, and then we went back in time 1 hour and 2 hours and tried to say, all right, well, hopefully if we go back in time, we'll remove some of that convective contamination potential. The environment, I think Perils, a field campaign, is showing that the environment can change very, very quickly. So there's some caveats to doing that. But to try to get rid of the convective contamination, we went back 1 and 2 hours. And for the ZDR columns, even when we did that, there were still statistically significant differences at -1 and -2 hours. So we have pretty high confidence in this result that there would be taller ZDR columns when there's greater environmental instability. Another one was we saw stronger rotational velocity for measures of low level, or I'm sorry, of shear. But these statistically significant differences were not present at the -1 and -2 hours. So we have lower confidence in this particular relationship. Same can be said for this. We looked at KDP cores only for tornadic mesovortices in environments with high and low LFC and LCL. And in this case, we saw that the KDP cores were stronger for environments where there was low LFC and low LCL. And it took a little bit of thinking about this, but we think the reasoning for that is basically if you have low LFCs and low LCLs, your environment is less favorable for a stronger cold pool. You have to have a cold pool that is at least, decently strong enough to get that strong convergence on the updraft, downdraft convergence zone. So if the environment is not supportive of cold pools, then you would need a stronger KDP core, more cooling within the downdraft in order to get sufficiently strong enough cold pool and therefore outflow and convergence along the updraft, downdraft convergence zone. So this is just kind of goes back to that idea that, considering radar and near storm environment is probably beneficial and important, not only in QLCSs, but obviously across many different hazards. Similar to the rotational velocity, we did not see statistically significant differences at the -1 and -2 hours. So we have lower confidence in this result. And then last up was range. We wanted to look at range. Our max range that we looked at was about 160 kilometers. So we started breaking these down by, all right, what if we only look at mesovortices beyond 70 kilometers, beyond 80 kilometers? What happens to our distributions? This is an example showing mid-level KDP cores, where basically as you go further out in range, the differences in the distribution of KDP cores for tornadic and non-tornadic mesovortices decreases. You can see that in these p-values where they're low, oh gosh, close to statistically significant, and then no more statistically significant differences here once we go beyond 100 kilometers. And you can visually see that in the violin plots as well, as they all sort of, the tornadic and non-tornadic tend to get closer and closer together as you go further out. So what does this mean? Basically, the further out you are in range, remember we talked about mid-level KDP cores being stronger for tornadic than non-tornadic mesovortices, which could give some confidence in anticipating how strong the mesovortex might be. As you go beyond 100 kilometers, that difference goes away. And so that might impact the ability to anticipate mesovortex intensity. However, we did see that all of the radar signatures, except for -20C, 50 or 50 plus DBZ -20C cores, all of the radar signatures were still common with mesovortices, regardless of how far away they were from the radar. So I think that these radar signatures are still going to be present at greater ranges. So that could help in that anticipation of mesovortex development. It could still be a confidence builder. Okay, I have 3 or 4 confidence builders, including a KDP core. Even though the storm is way far away, it can still be a confidence builder to give some guidance about that warning decision. And then a little bonus I threw in here, we did look at the mesovortex rotational velocity of all of the different mesovortices that we looked at. And we did see that rotational velocity was stronger for tornadic mesovortices than non-tornadic mesovortices, damaging than non-damaging. As you go up in EF scale rating, the mesovortex rotational velocity was stronger. This is not a surprising result. It's already been shown in previous studies, but it was nice to confirm this expected result. If I had seen something totally different, it probably would have made me question everything that we did. But since we saw this, I think it gives more confidence to some of the other results that I've presented as well. And one somewhat interesting thing that I did want to highlight is looking at the rotational velocity between non-damaging and wind only. There's not a difference. So these differences between damaging and non-damaging are driven by the tornadic mesovortices. And this is different than those KDP cores. The mid-level and low-level KDP cores had differences between non-damaging and wind only. So it just keeps giving me more and more evidence that, these KDP cores might be, a pretty useful signature. I was all about them in downburst research, and now I'm really starting to like them in this QLCS work as well. All right, so I presented a whole bunch of information. I kind of just want to break it down as what I think all of this means, kind of my interpretation of the results. I think that there is promise to incorporating some of these signatures into the mesovortex warning system, especially KDP cores into it as a new confidence builder. I think it can help with anticipating mesovortex development as well as intensity and impacts especially as you get to see more and more of those confidence builders within the mesovortex warning system. I think, like I mentioned, KDP core is probably most useful. Part of that is because we saw those differences between tornadic and non-tornadic mesovortices, damaging and non-damaging, even EF2 versus EF0. Those low-level KDP cores had statistically significant differences between EF2 tornadoes and EF0 tornadoes. And that was the only radar signature that we looked at that had that. So I think KDP cores do show some promise. So really, if you have a stronger mid-level KDP core and a stronger and then strengthening low-level KDP core, remember there was that different trend, increasing trend for the tornadic mesovortices. To me, that would suggest a higher likelihood for a tornadic mesovortex. I think KDP drops are also helpful, can also be helpful and a good confidence builder. Not only did they precede many of our mesovortices, about 95%, but there was also that preferred development location. So this could give some kind of confidence or guidance in where should I place the warning polygon relative to this KDP drop. Obviously, these are rough thresholds and not silver bullets, because 25% of mesovortices still did occur on the right side of the KDP drop, but it's just building that confidence. ZDR columns, I think, are less useful. I don't know whether they would work well as a confidence builder. I think they can provide some guidance as to where the strongest portions of the line are, maybe where the strongest mid and upper level updrafts are. And maybe those strongest parts of the line might be where you have the highest mesovortex potential. But in terms of trying to get a warning type, should it be a severe thunderstorm warning or tornado warning, or how likely is it going to be a tornadic mesovortex versus a non-tornadic mesovortex, I don't think ZDR columns can really show much in terms of that. And then some of the single pole signatures I think could be potentially useful as well. That the spectrum width I think is a good diagnostic tool, where we saw that it was stronger for tornadic than non-tornadic mesovortices. They do form at the same time, about the same time as a mesovortex, maybe not a lot of predictive potential there, but I do think that they are a useful signature. And then reflectivity cores, we really just need more work here with different thresholds, but 50 dBz is not a good threshold to use for research or probably for operations in these QLCS environments. And then I really just want to hit on this again. I've talked about it quite a lot, but none of these radar signatures can be used in isolation. It's all about building confidence in a warning decision, which is really what the mesovortex warning system is all about. I do get questions about lead time a lot. Can mid-level KDP cores increase lead time? I mean, they develop before a mesovortex does, but if we start asking that question, then it's really, the answer is, I can only answer that if we consider these signatures in isolation from everything else. So I don't think they should be considered in isolation. So I guess my answer to the question is maybe. I think that, the key would be making sure the three ingredients are roughly met. You start to see some other confidence builders. Maybe even KDP cores are one of those confidence builders, but you see a Z drop, you see a surge. And then when you start to see those things, maybe then you jump up to the mid-levels, look for that KDP core, see how strong it is really quick, go back a couple volume scans, forward a couple volume scans, see how strong it is. This particular one has values near 6, and near 6 was above the 75th percentile of tornadic mesovortices. So maybe at this point in time, at 04, 30, 17, you have multiple confidence builders, you see this really strong KDP core, maybe that pushes you to a point where you can issue a tornado warning. And a tornado did develop at 04:36 in this particular event. So perhaps it would get you to a point where you could issue a warning sooner, but I really want to be careful about that lead time discussion, because none of these are magic bullets or able to, you can't just look at mid-level KDP cores all the time and issue warnings based on that alone. I don't think that would work very well. And then I think that, practice in West cases or some kind of training maybe is going to be most effective for application of the mesovortex warning system, including these dual-pol signatures, just because there is some subtle and subjectiveness to a lot of these radar signatures. And it takes practice. I know Jason talks about, certain signatures in the mesovortex warning system that I don't even see. Like, I'm like, okay, where is it? And he can point it out. And obviously through lots of practice and whatnot, he's really, really good at seeing that. Now I've gotten a lot better at identifying some of these dual pole signatures than I was when I first started the research. So it just takes some practice and training, I think, to get all of this, really well incorporated in your own personal conceptual model. So with that, I want to thank you all for your time and attention. These are some of the kind of big conclusions that we had. I've got my contact information up there at the bottom if you have any questions or want to reach out with feedback, or maybe you think I did or said something totally wrong. I definitely want to hear about that. And then I also put the QR code here as well. If you scan that, it'll take you to that interactive presentation. I plan to keep that up to date. That's really just kind of a living resource that you can go to see the most up-to-date results from this particular research. So once again, thank you for your time, and be happy to take any questions if there are any, or if there's time. All right, let's see. Aaron.
Hi, Charles. Hopefully you can hear me.
Yep, I hear you.
Great presentation. So a couple things. First, I just want to get some clarification. If you could go back to as early on in your slides where you were showing, like in a table, percentages of, I think it was low-level and mid-level KDP, TOR versus non-TOR. I just want to make sure I'm interpreting that correct, because the numbers, when I first looked at it, looked almost identical. Yeah, like that.
Yeah.
So I mean, I'm trying to figure out how to really take that, because they look identical, and so then I'm left with wondering, well, if tornadic and non-tornadic are identical, how do I interpret that? Because it seems like the features are always there, and so then I guess that leads to a follow-on, and just more of a question comment for you. I see, within the various, especially the graphs and showing the box and whisker plots, there is separation that I think statistically is relevant. I think we can see that. The question I have, though, is in many cases, the values within KDP are within 0.5 or 1. And at least from an 88D perspective, that can be noise. So I guess I'm trying to figure out that if the difference is there statistically, but it's so small, it kind of reminds me of things with velocity, where there is a statistical signal, but it's not necessarily something we can use operationally because it's such a small margin of error. And I get that plays into the whole, you use this collectively, but I guess those are the two things I kind of was struggling with was, okay, if the numbers are the same, but the main difference is these small difference in values, how does one reconcile a variance of 0.5 as being something they can find? Because a lot of people are not going to be staring at the pixels of KDP each scan. So I hope that makes sense. It's a great presentation. I'm just trying to make sure I understand all this.
Yeah. No, those are great questions, and stuff that myself and other co-authors here have talked about a lot. Like how can this or should it be used? So to your first point, and I should have mentioned this, is a lot of the mesovortex warning signatures, mesovortex warning system signatures, they're mesovortex signatures, not tornado signatures. So they're trying to build confidence in mesovortex development. And then as you get more and more of those confidence builders, that's when it can start to push you towards, okay, maybe this will be a tornadic mesovortex. So these signatures, whether it's a ZDR column or a KDP core, they are common with both, they're common with mesovortices. Whether they're tornadic or non-tornadic, they exist. And I mean, I think that makes sense where, if you have a surge in the line and your 3 ingredients are met, odds are there's going to be a mesovortex, unfortunately. So that's where it comes to, like, this is a mesovortex precursor. Then the next step is, all right, with either number of confidence builders and nudgers or with magnitude, can we then get to a point where we can say, okay, this particular surge in the line deserves a severe thunderstorm warning, or this particular surge in line deserves a tornado warning. And so that's where, at least, and I'm curious what you think about this. So in the paper that we're working on, we proposed some thresholds. So instead of, instead of trying to figure out, okay, what's my, I think there are a couple of things that you could do, but we put forward some thresholds. So we used the 75th percentile of the non-tornadic KDP core, which I think was just above 5. And we said, okay, that sits below the median for non-tornadic. So you could potentially miss some tornadic, but at least you're going to be out of the non-tornadic range. So if you see at any point in time a mid-level KDP core magnitude of, let's just call it 5.1 or higher, that could be your confidence that, okay, this is more likely to be a tornadic mesovortex than a non-tornadic mesovortex. So that's where I would kind of try to build this in. Another thing you could do is just, have these violin plots up. You're starting to see confidence builders. You see a low-level KDP core and its magnitude is 3. All right, let me look at this. Maybe this would be on a one-pager. What does 3 mean? 3 is way down here. Okay, well, I don't have a lot of confidence that it's really going to do much of anything, right? So maybe I don't want to issue a warning. Or maybe you're starting to see some confidence builders and you look and you find the mid-level KDP core has a magnitude of 6. I talked about that with the one that produced an EF2 tornado. Its magnitude was close to 6. If you come to 6, and you see on these violin plots, oh man, this is above the median. It's well above the 75th percentile. I have these other confidence builders, and my KDP core magnitude is 6. Tornado warning time, something like that. And obviously 6 would be above the threshold. That might be a little bit easier, if you just have a threshold of, all right, I've got 5 in my mind. If I see something above 5, it's a confidence builder for a tornado warning, something like that. So that's maybe where I was thinking, where we as a team were thinking in terms of this. But I hear, or at least see, that there are other hands raised. I'm curious, Aaron, if you have any thoughts, and then I think, let's see, John has also got a hand raised as well in here.
Yeah, I appreciate all that, and I'll not try to hog all the time here. The main challenge, I guess, I was trying to infer was not that statistically we can't see that, say a value of 5 is relevant. The challenge, and we get this with really anything, is how reliable or how consistent, what is the error rate of the 88D to differentiate something where, a value of 4.5 versus a value of 5.5. Will somebody notice that? Is that even reliable? If we were talking about a KDP of 2, let's say, versus 6, game on. But I guess that was my thought there was, we see a lot of statistically relevant stats and studies, and we've seen that with things like VROT, but a lot of these, the error rate, even with the 88D at like just a few kilometers, starts to exceed what the difference in the statistical data shows. And I guess that was just kind of my main thought. So anyway, great presentation.
Yeah, no, I agree, and that's really important to bring up, like, the difference between statistical significance and operational significance. And there are, I mean, honestly, for KDP cores and downbursts, there were smaller differences between what I called strong downbursts and weak downbursts, where it was in that like 0.5 degree range. And I was like, okay, well, this may be statistically significant, but it's not operationally significant. So that's a really good point to bring up. I will say I've worked a couple rack cases for downbursts and used the threshold idea. I gave some wiggle room, but I had like a threshold idea of, okay, if I see a KDP core of this magnitude, I'm expecting a storm report today. And it worked pretty well. Like I feel pretty good about KDP cores and being able to use their magnitude to anticipate various hazards. But we do need to be careful and figure out what is the wiggle room that we're willing to have, the error bars that you talked about. That's a very, very good point. And I think something that we need to continue working on. John.
Hey, Charles, great presentation. Good to see you again. Hey, just quickly, actually, I have a number of questions, but I'll try not to hog all the time. When you talk about a KDP core, kind of a follow-on to Aaron's point, it appears as though you're looking at a single pixel value. I guess, do you have an aerial threshold at what you consider to be a KDP core? The reason I ask that is because, you can make a lot of individual pixels that may or may not be an accurate microphysical explanation for that KDP value, if, what I mean. So I was just curious about, what you're looking at, if it's individual pixel value or something more. And then I have another question after that.
Yeah, the KDP core itself, I didn't have like an aerial threshold that I applied, but what I can say is it's much more than 1 or 2 or even 10 pixels to call it a KDP core. It's if you just see kind of random noise everywhere and it's not coherent in space and time, then I wouldn't call that a KDP core. The KDP cores tend to be relatively continuous in time, even in height, trying to think of distance across it would have to be at least a couple kilometers, I would think.
I guess the question I'm asking is more to do with the max value that you're referring to.
Sure. Yeah. Yeah. So when looking at the maximum value, it could be as small as 1 pixel. I basically would have used some subjectiveness to be like, okay, is this value of 10? Is this an error or is this realistic? Kind of like what you might do with velocity. If you see some crazy hot pixel of inbound velocity, do you include that in your calculation of rotational velocity in impact space warnings? Probably not. So I was kind of doing the same thing where, all right, this has to be a reasonable maximum value. Otherwise, I'm not including it in my analysis to try to get rid of that noise. But yes, it could be just a one pixel. But if I have a whole bunch of 4, between 4 and 4.5 pixels and one of 8, I'm probably not including that 8.
Okay, yep, makes sense. The other question I'll ask, as I see Andy has his hand raised too. The fact that the KDP drop and the mesovortex occurs primarily or favors the left side of that. Curious if you think that may be a result of the river bend effect, similar to some of the theories presented in supercells, E.G. Roberts et al. From earlier.
I think that's distinctly possible. I'm not entirely sure. I haven't come up with like a good explanation for why the left side is favored. I think that's definitely a reasonable hypothesis. I think that's something that maybe some high-res models maybe are going to look at. I don't see a whole lot in the literature right now to suggest why the left side would be favored. I don't know. Does anyone on here have any thoughts? That's a really good question. I see Andy's got a hand up.
Hey, Charles, we have a different question. It's not related to what you were just talking about.
No worries, no worries. I think unless anyone has anything that they want to put forward, I don't know, Vivek, if you have any thoughts about that, we can go on. I definitely need to put some more thought into that.
Yeah, I mean, I think we've seen it all the time that it's like the orientation on the left side with the shear becoming perpendicular. So I don't know if it goes kind of back, at least here in the plains, what we see when we have a strong low-level jet, when you have that bowing segment, the north side of that low-level jet is when your low-level shear is kind of perpendicular to the, essentially the bowing on that side. It becomes perpendicular because you get more of a normal component. So I think it has something to do with that. I think connected to that, because at least here, usually it's a north-south oriented bow, but once you get that surge, the left side, you're going to now have a line normal component. So I think it increases the line normal component to a lot of times a low-level jet, at least here I've noticed here in Oklahoma.
That's a really good point. Yeah, Jason is putting on, the conceptual models, like the left side with how the line is oriented is probably just better for the 3 ingredients method overall. So that's a really good point. Thank you guys for bringing that up.
The 3 ingredients method, can be modified by the storm scale. If the storm scale surge occurs, that essentially changes, your component of where your line normal is. So if you have a surge, you're reorienting that shear vector essentially.
Yeah. All right, go ahead, Andy.
Yeah, Charles, thanks. Great presentation. We appreciate it. Mike here has a question.
Yeah, hey, my mind kind of goes to the Atkins and Laurent conceptual model. The rear inflow jet infers descending parcels that acquire horizontal streamwise vorticity. That when getting near the surface, those parcels tilt and stretch into the vertical, or something like that. We see this in radar with the disappearing reflectivity. And so my question is, do KDP cores, whether low or mid-level, would those precede the disappearing reflectivity confidence builder signature, or is it just another way of looking at it?
I think that the mid-level KDP cores could precede that. The ZDR columns and KDP cores tended to develop first. And then shortly after that is when you started to see evidence of the KDP drop, which would be kind of that descending rear inflow jet and the kind of Z, lowering Z that you're talking about. So mid-level KDP cores, I think, could precede that. My thought with those mid-level KDP cores is that you're getting a locally enhanced area of stronger downward motion within your rear inflow jet. Which one of those comes first? My guess is rear inflow jet, and then you just have some kind of storm scale downdraft thing that's going on that leads to a localized stronger area within the rear inflow jet. So for the most part, especially low-level KDP cores, I think that's just another confidence builder alongside that, but the mid-level KDP cores could come first. But I think all of it's kind of trying to build to the same point. But mid-level KDP cores, I think, are better suited to come before that signature.
Thanks. Thank you.